25 million people move through this dense grid of traffic, commerce, and neon, relying entirely on a constant, uninterrupted flow of surface-level power. If every one of those municipal utilities suddenly ceased to operate tomorrow, it is easy to assume the entire metropolis would simply grind to a halt. But the actual lifelines of Shanghai operate beneath the asphalt. Directly under the feet of its residents lies a completely separate network, actively pumping water, logistics, and data through the dark. We are accustomed to subterranean spaces moving passengers on trains. This is a different classification of engineering entirely, designed to move the vital functions of the city itself. These corridors represent an effort to reorganize the city's foundational systems around a vertical rather than horizontal axis. The paradox of urban development is that as a city matures, its ability to maintain itself degrades. The older the grid, the harder it is to execute a simple repair. A single ruptured water main rarely stays a localized issue. Fixing it requires tearing open the pavement, which chokes arterial traffic, disrupts local commerce, and triggers severe secondary economic costs. Legacy cities like New York and London frequently find themselves locked in this reactive cycle, forcing engineers to place temporary patches over aging systems. This cross-section shows municipalities layering utilities haphazardly over generations. The subterranean profile becomes a tangled web of 1920s cast iron, resting on 1990s fiber optics. Sharing no unified space, telecom, gas, and water providers must independently excavate the exact same road. The physical pipes rarely fail on their own. It is the fragmented, chaotic layout of the dirt itself that prevents proactive maintenance and guarantees perpetual gridlock above ground. By the late 1990s, an intense population surge pushed Shanghai's surface infrastructure to its absolute limit, resulting in severe pedestrian and vehicular congestion. Planners quickly found that natural geographic boundaries and surrounding suburban settlements left no available land to stretch the city's borders horizontally. Stacking millions of additional residents into increasingly taller skyscrapers only compounded the density crisis at the ground level. Facing severe spatial exhaustion, the municipal government mandated a radical pivot, the permanent cessation of outward expansion in favor of extreme depth development. With horizontal expansion blocked and vertical limits reached, the dense earth beneath the streets became the final available territory for the city to grow. Shifting to deep earth excavation required carving massive industrial footprints directly into the middle of heavily populated commercial zones. Engineers immediately collided with the local geology. Shanghai is built on an exceptionally soft alluvial soil, heavily saturated by a high water table. Boring a tunnel through this environment offers immense physical resistance. The ground behaves less like solid rock and more like thick, wet cement. Early tunneling attempts in the 2000s met severe setbacks. Groundwater routinely flooded the excavation shafts, and several surface areas experienced alarming levels of subsidence. Instead of abandoning the initiative, structural engineers utilized these ground collapses as strict data points, forcing the implementation of highly aggressive, sensor-driven safety standards. What began as brute force excavation evolved into a delicate, continuous negotiation with the structural integrity of the city's bedrock. The completed architecture bears no resemblance to a dirt trench. It is a stark, brilliantly lit, multi-tiered concrete vault. This diagram illustrates the corridor's organization. Engineers isolate electricity, municipal water, high-pressure gas, and data lines. Technicians walk alongside them, repairing cables without lifting a shovel. This tunnel connects to a digital control room, where operators monitor every utility simultaneously. The investment follows a dig-once logic, providing permanent maintenance access without ever disturbing the surface. The network acts as a physical operating system, allowing the city to swap or upgrade utility hardware as technology evolves. When the chaos of construction and maintenance is entirely buried below the concrete, you have to wonder how that undisturbed quiet shapes the daily lives of the millions of people walking above it. When severe flooding hits a standard urban grid, the consequences are immediate. Water overtakes the exact arteries a city relies on to function. This triggers a cascading failure. A flooded street halts traffic, which severs supply chains, traps emergency services, and zeroes out local economic output. Because these surface-level systems are completely exposed to the elements, engineering, a disruption-resistant alternative, is an absolute requirement for long-term survival. Beneath the feet of those residents lies a massive, highly organized concrete foundation. This network isolates high-voltage electricity, water mains, fiber optic internet, and automated logistics from the elements above. It also absorbs the daily transit of millions of people, pulling mass commuting into an enclosed, climate-controlled environment. Engineers call this redundancy. By building duplicate, isolated systems away from surface weather, they ensure the city's power supply lines remain active, regardless of what happens outside. Today, these tunnels operate as a complete parallel second city, engineered explicitly to keep the urban core alive. Shanghai is part of a broader national strategy. Cities like Beijing, Shenzhen, and the newly developed Xiong'an are all integrating this model. Carving out this subterranean frontier requires specialized heavy industry, utilizing massive tunnel boring machines to bore through bedrock and soil. In newer development zones, urban planners apply an infrastructure-first philosophy. The complete subterranean grid is excavated, mapped, and installed long before a single residential building is erected. It is a complete departure from organic urban growth, prioritizing a hyper-planned foundation over surface development. Compare this to the friction experienced by metropolises built over a century ago, where essential infrastructure is buried directly beneath active streets. When a legacy water main requires repair, public works teams must break through the asphalt, shutting down major thoroughfares and creating bottlenecks that ripple through the local economy. This split-screen bar chart compares infrastructure downtime. On the left, surface-level repairs show a high frequency and long duration of traffic disruptions. On the right, subterranean utility tunnels require near zero surface interruption for the exact same maintenance. The divergence here is a philosophical choice. Perpetually patch a century-old system or engineer a clean slate foundation built to operate uninterrupted for the next 50 years? Pushing the machinery of a city downward creates immediate physical consequences on the surface. When utility repairs, heavy transit, and logistics networks are removed from the road, a significant amount of industrial friction disappears from daily life. Planners use this newly freed square footage to expand pedestrian zones and cultivate expansive green spaces. Through this spatial inversion, the city's mechanics move downward, allowing nature and human activity to expand on the surface. The final result of this engineering is the ability to walk through a dense urban center and see trees instead of traffic. Overcrowded urban populations, volatile climate events, and rising maintenance costs are forcing nations around the world to reconsider how they build. What is happening in China's new urban zones is a live test of an invisible foundational model for the 21st century metropolis. When the critical infrastructure that keeps a city alive becomes entirely hidden, we have to ask if a skyline is still the best way to measure success. If you had the opportunity to design a new city from scratch, would you want it to grow upwards toward the sky or downwards into the Earth? Share your perspective in the comments.